myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, we are going to continue with the microwave measurement part 3. In this section, first of all, I am going to discuss with you return loss measurement. So, whenever we talk about the return loss, what is meant by the return loss? Whenever we give a signal to something and it is not fully absorbed by that and it get reflected back, that is our return loss. So, if we want to measure it, what we have to do? Return loss is also known as the reflection loss and is a measure of the fraction of power that is not delivered by the source to the load. Same thing, the power which we are going to deliver to the load, it is not fully received and it is reflected back and it is called as our return loss. So, if the power incident to the load is given by Pi and power reflected by the load is given by Pi, then in that case the return loss which can be measured in the terms of decibels is written as 10 log Pi upon Pr, where Pi is the incident power on the load and power Pr is the power reflected by the load. So, already we have discussed this previously also, that this returning of power occurs in the case of non-matching or we can say non-matched load, and it basically tells us how much matching is between the source and the load. If the matching between the source and the load is perfect, that is impedance of source is equal to the impedance of the load, in that case there is no return loss. Or so, and as the matching between these two goes on decreasing and it tends towards the non-matching condition of the impedance, our return loss keeps on increasing. So, this is basically the concept of our return loss. So, the better the load is matched to the source, the lower is reflected power and hence higher the return loss. RL is positive quantity if the reflected power is less than the incident power. If the load has a complex reflection coefficient rho, then in that case the return loss is given by 10 log 1 upon rho square. If we are provided with the return loss, in that case we can directly have the value of our return loss in dB, which is equal to minus 20 log rho. And if we are provided with the value in the terms of power, reflected power and the incident power, then we will go through this formula. So, what the formula you are going to use for the return loss measurement depends upon the value available with you. If the power value is available with you, kindly go with this formula, and if the reflection coefficient value is available with you, then go with this formula. Return loss is negative of the input reflection coefficient expressed in decibels. Now, here is a two-port network, and two-port network return loss is defined with respect to the input reflection coefficient. So, here we have used the term that the return loss is the negative of the input reflection coefficient expressed in decibel. So, now we are going to calculate our return loss in the terms of input reflection coefficient, and in the terms of the input reflection coefficient, the two-port figure, the input reflection coefficient is given by tau n and it is equal to S11 tau L S12 S21 1 minus tau L S22, where tau L is our reflection coefficient of the load. So, if we want to define the return loss in the terms of the input reflection coefficient that is given by the tau n, what the parameters which we are required? First, we require the tau L, that the reflection coefficient of the load, and if we have a two port network, we can have the S parameter as S11, S12, S21, S22. This parameters we can obtain with the help of a network analyzer, and also with the help of two coupler. About that we have already discussed in our last lecture, where we have calculated the scattering matrix of any microwave devices. So, if we are available with the our scattering matrix, which can be measured with the network analyzer and two coupler. So, for that you can refer to our previous lecture of the microwave measurement, and so now we are available with the S11, S12, S21 and S22, and we can apply that here, and we are able to get the input reflection coefficient. So, when we are able to calculate the input reflection coefficient, we can calculate the return loss of a terminated two port network with this formula -20 log tau n. And of course, when we expand the formula of the tau n, the complete expression is like this, where we have just substituted the value of tau n, which is obtained here, into the final expression. And again the condition comes when the system is perfectly matched. Here we have seen that this formula is applicable for the terminated load. Already we have known there is a condition where the load is attached, and when there is, that is called the terminated one, and when the load is not attached here, then when this ZL is missing, then it is called as the non-terminated. So, if this is a general expression for the terminated load, but in the case the terminated load, that is ZL, is equal to the conjugate of our characteristic impedance, or we can say the matched condition. In that condition, our return loss is directly equal to -20 log S11. So, this is the general expression of return loss, because we can apply that this in various type of microwave measurement or RF technique. For example, even for the antenna measurement technique, which we normally use in the case of our antennaized designed microstrip antenna, what we are able to calculate to get the return loss? We just calculate the S11. On the basis of S11 only, we judge that what will be the return loss, because what is that in that case? Because we already terminate, we use the 50 ohm impedance always for feeding or etc. So, we are actually providing a matched condition. That is why in all the measurement system you are able to know कि S11 is our return loss. In general communication language we can say कि S11 is our return loss, but you have to know that S11 is the return loss only when the condition is matched. If you are not providing the matched conditions of the system, in that case this is not possible that S11 is our return loss. We have, for an unmatched condition, we have go to the complete expanded expression of the return loss. So, return loss is also called the input return loss, and the reflection coefficient is calculated at port 1, because how much power is received back by the port 1, we calculate that. That is why it is called as the input return loss. Output return loss is when how much power is received at the output. In that case, at the place of S1, we use the term S22. We can get the value of S11, S12, S21 and S22 from the scattering parameter calculations about that, which we have discussed in the previous lectures. So, kindly go through that. if you want to just the division of the how we are getting the S parameter values. Now comes the impedance measurement. Impedance measurement is one of the most important parameter in the measurement of the our microwave devices, and in this case we are going to use the three techniques for the impedance measurement. First one is the magic T, second one is the slotted line, and third one is the reflectometer. Reflectometer is a device, magic T is our passive component. About that which we have discussed already in the unit 2 of our microwave and radar engineering subject, and slotted line is a general line in the microwave test bench. We have done various measurement with the help of a slotted line. Now first using the magic T. So what is the principle of the magic T? Magic T is the combination of E plane T and the H plane T, and it is a 4-port device. So what we are going to do in the one of the thing which I must want you to remember, that collinear ports, in the collinear ports signals are not received. If we provide, for example, if we provide the signal to the Z1, it will not received by the, if we provide the signal to, for example, port 1, it will not received by the port 2, and if we provide the signal to the port 3, it will not received by the port 4. This is the magic behind in the our magic T. So keeping this point in mind, we are going through the calculation part of the magic T and how we are going to get the impedance value in the case by using magic T. So what we are going to do here? In the port 2, we are keeping the that component, or we can say that load whose impedance we want to measure. So in port 2, we are keeping the unknown impedance or the load whose impedance we want to know. And in port 1, what we are giving? We are giving a standard variable known impedance, means the impedance who a value or a device or a load whose impedance is known to us and which can be varied also. So standard variable known impedance is kept at the port 1, and at the port 3 we are providing the microwave source, and all the microwave source already we have discussed. You have discussed about the klystron, you have discussed about the our various types of TWT, etc., which all comes under the category of microwave source. Normally in the measurement purpose we use the reflex klystron as a microwave source, or here we are providing a null detector. So what we now going to happen here? We are providing a signal of A3. We are providing a signal of A3 from the port 3, and it is distributed to the port 1 and the port 2, it will not go to the port 4. And how we are getting the value of 1 by under root 2? You are get the answer of this from the matrix of the or S parameter matrix of the magic T, which we have already discussed in the unit 2 where we have discussed about the magic T. Just take a look of the expression of the S parameter of a magic T. Then in that case you are able to get that if the signal is provided in the input is given from the port 3, then it will give divided into the port 1 and 2 by the port 2 by 1 by under root 2 A3 and 1 by under root 2 A3, that is equally. And now it is get by the Z1 and Z2. So there is of course a impedance mismatch between here. So due to this, the reflection coefficient of Z1 is the rho 1. So all the power does not get transferred to the here. The power received by it is 1 by under root 2 A3 rho 1, and similarly here the power received is 1 by under root 2 A3 rho 2, where rho 2 is the reflection coefficient of Z2. And now this power is transferred to the null detector, and when the signal is transferred from the port 1 to the port 4 and port 2 to the port 4, what is happening? 1 by under root 2 power of the port 1, that is 1 by under root 2 A3 rho 1, or here with a negative sign, that means this is our E plane port, minus 1 by under root 2 and power of the from this port 2, that is 1 by under root 2 A3 rho 2. So, what is the function of the null detector? The function of the null detector is that we have to at the point of 4, a port 4, when we add this 2, the resultant will be equal to 0. So, the net wave reaching the null detector is just I am going to have it, and it is equal to 1 by 2 A3 rho 1 minus rho 2. Then what is the perfect balancing condition? That is, this null detector should be equal to 0. So, if we make the null detector equal to 0, what we are going to do? We will make this expression equal to 0, and when we make this expression equal to 0, this term gets 0 and rho 1 minus rho 2 is equal to 0, or rho 1 is equal to rho 2. And we know that reflection coefficient is written as Z1 minus ZZ upon Z1 plus ZZ, where this is our characteristic impedance, Z2 minus ZZ, Z2 plus ZZ. So, by cancelling, by solving this equation, we are able to get Z1 equal to Z2. So, what is the main purpose here? That we have to vary the impedance. Which impedance? The impedance which is present at the port 1, till that we are able to get the 0 value at the null detector. So, at the point when we are getting the 0 value at the null detector, at that point whatever be the impedance at the port 1 will be the impedance at the port 2. In that case, we were able to calculate the impedance, unknown impedance at the port 2. So, we have to vary the impedance at the port 1 till our null detector show us 0 value. So, we are not going to do this much of calculation for getting the impedance. We have to just vary we have to make the arrangement and keep on varying the port impedance, variable impedance kept at the port 1 till that the null detector show a 0 reading. And the value of the impedance which is showing at the variable impedance at the when the null detector is showing the 0 value is the value of the impedance of the unknown load. Now, using the slotted line. So, what we are able to get the slotted line? So, first we are in this case we are actually making the two type of arrangement. First is the arrangement determine V min using the load ZL, and in the second step we are actually short circuiting the load and again calculating the V min. So, the arrangement of the setup should be like this: microwave source, attenuator, slotted line, crystal detector, power meter, unknown load. And here microwave source, attenuators. So, what we are getting? We are replacing in the second setup of the measurement this unload load with the shorted termination. So, now we are getting this type of load. If we first of that is the V min we are actually getting, and this is the condition for the setup 1 when we are using the load ZL. In that case, this is our waveform which is received and this is our V min for example. And in the setup 2 when we have short circuited the termination, if what is this side called? This is our left side. So, when in the case of a short circuited termination, now if our V min shifted towards the left, then in that case the load which we are taken in the setup 1 should be a inductive load. Again I am repeating, we are in the setup 1 we are attaching the load, and in the setup 2 we are providing the short circuit termination. And if in the case of a setup 2 when we are providing the short circuit termination, if our V min is shifted toward the left, then the load which is used in the setup 1 is basically a inductive load, and if our in the setup 2, if the V min gets shifted towards the right, then that is, in that case the load is capacitive in nature, and if there is no shifting, then of course the load will be resistive in nature. So, that is mentioned here. First of all, either we can calculate, I have shown you the result in the terms of V min, you can take the V max also. So, first using the load, second by using the short circuit termination, the minimum gets shifted either to the right or to the left. If to the left, this means the load is inductive, and if to the right, it means the load is capacitive. So, by this method we are able to get the inductive and capacitive nature of the load. Now, the third method for the measurement of the impedance, that is using the reflectometer. So, unlike the slotted line, the reflectometer helps us to find only the magnitude of the impedance and not the phase angle. In this method, what we are going to use? Two directional couplers which are identical, but directions are different. So, if you are able to see this, we are taking a two directional coupler which are identical, 20 dB and 20 dB, but this is a forward directional coupler and this is the reverse directional coupler. So, basically both the directional couplers are of 20 dB, but one is a forward and second one is the reverse. The two couplers are used in sampling the incident power Pi and the reflected power Pr from the load. So, what we are going to do? The setup should be like this: microwave source, attenuator. I think all of you should know the purpose of an attenuator. We just to lower down the signal level. Forward directional coupler, reverse directional coupler, and a load. What is going? We are able to calculate, get the coupled output here, which is given by Pi upon 100, and where here also we are able to get the coupled output, and that is equal to Pr upon 100. And when this both are given to the reflectometer, then it gives the rho in the terms of under root Pr upon 100 upon Pi or Pf upon Pi upon 100. So, no, 100 get cancelled and our rho should be equal to under root Pr upon Pi, and we know that S is equal to 1 plus rho upon 1 minus rho, and if rho is also equal to Z minus Zz upon Z plus Zz, where Zz is the known wave impedance and Z is the unknown. So, we are able to get the value of rho from the reflectometer, and Zz is the known wave impedance. So, we can easily find out the value of the Z, which is our unknown impedance. So, by these three methods we are able to calculate the impedance. Now, the measurement of the VSWR. The VSWR is measured by is basically our standing wave ratio, and it is given by the ratio, it is the ratio of the Vmax upon Vmin, which is also equal to 1 plus rho upon 1 minus rho. And what is our rho? That is our reflection coefficient, and it is equal to P reflected upon P incident. And measurement of VSWR can be done in two ways, that is low VSWR and high VSWR measurement. In the case of a low VSWR measurement, can be done by adjusting the attenuator to get a reading on a DC millivolt meter, which is our VSWR meter. So, we can measure the VSWR less than 10 with the help of a VSWR meter. About that we will discuss in the next lecture. The reading can be taken by the adjusting the slotted line and in the attenuator in such a way that the DC voltmeter shows a full scale reading as well as the minimum reading. So, with the help of a VSWR, we are able to get the value of the VSWR directly in the VSWR meter, and nowadays both the analog and the digital type of VSWR are available in the market for the measurement of VSWR less than the 10. And for the measurement of VSWR greater than 10, we have to follow the technique of a double minima method. The measurement of high VSWR whose value is greater than 10 can be measured by a method called a double minima method. In this method, a reading at the minimum is taken and the reading at the half point of minimum value in the crest before and crest after also taken. This is the minimum value and we are able to half minimum at this point and we check the value in the slotted line ki what will be the this. We are able to get the D1 and D2. So, what in the double minima method, what we are going to do actually? We are first of all getting the minima. We are actually VSWR standing wave is obtained and here the minima. We take the half power point at the both the position. So, in the slotted line we check the value at what point we are getting the half power point of the minima, which is represented by D1 and D2, and by using this we are able to get the able to calculate the VSWR. So, we are getting the D2 and minus D1 and VSWR can be equal to lambda g upon pi D2 minus D1. So, D2 minus D1 can be obtained by the double minima method and lambda g, which is our guided wavelength, can be obtained by this formula. And this formula is already known to you, which we have discussed in the waveguide, and if you know the waveguide parameters which we are using in the microwave test bench, we can easily calculate the value of the lambda g with the specification already provided with the test bench. So, here comes the end of the VSWR measurement part and the microwave measurement part 3rd. We will continue with the microwave measurement part 4 in the next lecture. Thank you.